For this project, we chose to solve for the velocity field of the modified Couette flow shown in the figure. We assume that the velocity of the moving wall is 20 meters per second, the height of the first fluid is 5 millimeters, and the height of the second fluid is 8 millimeters. The first step was to open the program. From the Start menu, search for Workbench. From this window, choose Fluid Flow Fluent and drag it to the right. In our case, we named our simulation Modified Couette Flow. Now choose Geometry to start sketching the problem. We drew our problem on the XY plane. To choose that, click on the Z arrow on the bottom right. Then, from the Sketching tab, show the grid and choose the units to be millimeters. Start by drawing a simple rectangle. This represents our first fluid. Since the problem mentioned that the plates are infinitely long, we set them to be bigger than the height by more than one order of magnitude, or more specifically, 100 millimeters. Then we set the vertical height of the first fluid to be 5 millimeters. Our next step was to turn this sketch into a surface. From the Concept tab, choose Surfaces from Sketch, select the edge of the surface, click Apply, then Generate. Then choose Add Frozen. Start a new sketch for the second fluid. Draw a rectangle the same way as for fluid 1. Set its height to be 8 millimeters. Then once again, turn that sketch into a surface. Make sure that both surfaces are fluids. Make sure to always save your progress. The next step is to generate a mesh. Click on Mesh, then from Mesh Control, choose Sizing. Set the geometry selector on Edges, then select all the horizontal edges. Don't forget to select both planes for the interface edge. Then click Apply. Set the type of the sizing to be number of divisions. We chose a fine mesh of 300 divisions. The finer the mesh, the more accurate the results. Then choose another sizing and repeat the steps for the vertical edges. This time, choose the number of divisions to be 25. And make sure that the behavior of both the sizings is set to hard. Now from Mesh Control, choose Face Meshing and select both fluids. Click Apply, then click on Generate Mesh. After the mesh is generated, name all the surfaces and edges. Name all the inlet and outlet edges as periodics. This automatically sets the flow to be fully developed. Name the bottom plate wall. And name the top plate moving wall. Name the edges in the middle interfaces. Don't forget to name the edges on both planes. Set the geometry selector on planes and select each fluid and name it accordingly. Click Update to ensure that all changes have been saved. You can now close Mesh and move on to Setup. Select Double Precision for more accurate results. Make sure to select Pressure-Based, Absolute, Steady, and Planar. Under Models, make sure that Multi-Phase is off. Then move on to choosing the materials. In our case, instead of opting for already existing fluids, we chose our own and assumed the density and viscosity for both. From the Fluent database, we chose any fluid, then changed its properties later. For one of the fluids, we chose the density to be 1000 kilograms per meter cubed and the viscosity to be 1 kilogram per meter second. And for the other fluid, we chose the density to be 800 kilograms per meter cubed and the viscosity to be 2 kilograms per meter second. Then under cell zone conditions, we chose the first fluid, the one on the bottom, to be the denser one, and chose the second fluid to be the less dense. Under boundary conditions, make sure that the periodics are of type interface. Then, edit the properties of the moving wall. First, make sure that it is moving and set its absolute speed to 20 meters per second. Then, from Mesh Interfaces, manually create an interface. Give it a name. Set the option to Matching. Then choose the interface between the two fluids. Press Create and Edit to automatically create another one. Again, name it, but this time choose Periodic Boundary Condition under Interface Options, and choose the periodics of the first fluid. Create another interface and repeat the process for the other fluid. Under Monitors, set the residual. In our case, we chose it to be 10 to the minus 4. The smaller the residual, the more accurate the results. Initialize the solution, then run calculations. We chose the number of iterations to be 10,000. And calculate. Our results converged after over 1,000 iterations. Create a contour of velocity. Choose all the surfaces, make sure that the contour is filled. As expected, the contour shows that we have maximum velocity at the moving plate and zero velocity at the bottom plate. Create an XY plot that shows the velocity. Plot the two periodics on the outlet. As expected, the plot shows that there's a change in the slope at the interface between the two fluids, showing that the slope changes with the change in viscosity. This is another contour of our results that shows the velocity vectors of the flow and how they change throughout the two fluids.